Today's video brings you some familiar examples of law of conservation of linear momentum. As we have already discussed this law of conservation of linear momentum in my previous video, let me recall once again. For an isolated system, the total momentum before collision is equal to the total momentum after collision. As we know, an isolated system means the net external force acting on the system is zero. So this conservation law is valid for an isolated system only. If you want to know more of this law, please go back to my previous video on the law of conservation of linear momentum. Let me make you more familiar of this conservation of linear momentum from some examples given as follows. Example 1. Recoil of a gun. So what is recoil of a gun? You might have seen in some movies when a shooter fires bullet from his gun at a target. After firing the bullet, the shooter feels a backward jerk from his gun. This backward jerk or backward movement or backward motion of this gun after firing is called the recoil of a gun. Now let us see whether we can apply this law of conservation of linear momentum on this system consisting of the gun and the bullet. How does a bullet fired from a gun? Well, we know as soon as we pull a trigger, there's an explosion of the gunpowder. The forces caused by the explosion of the gunpowder are much larger than the force exerted by the hand. Therefore, the system is practically isolated one. So, we can apply law of conservation of linear momentum to this system as it is an isolated system, that is, the gun and the bullet form an isolated system. As we can see, before firing, the gun and the bullet are at rest. Therefore, their initial total momentum before firing is zero. Thus, by conservation of linear momentum, the total final momentum after firing must also be zero. Now, we shall try to express this in a mathematical expression. For this, let us take capital V be the velocity of the gun, small v be the velocity of the bullet, capital M be the mass of the gun, and the small m be the mass of the bullet. Now, by conservation of linear momentum, we know initial momentum is equal to the final momentum. Now we shall try to calculate the initial momentum of the system, that is, system consisting of gun and the bullet. So we know the gun and the bullet being at rest, their velocities are zero. So their initial momentum must also be zero. By conservation of linear momentum, we know that the initial momentum and the final momentum should have a constant value. So in this case, the initial momentum is already zero. This means that the final momentum should also be zero. So in this case, we have capital M into capital B plus small m into small b equals to 0. This implies that capital B equals to minus m into small b whole divided by capital M, which is the expression of the recoil velocity. That means capital B represents the expression of the recoil velocity of the gun. And here, the negative sign denotes that the gun and the bullet are moving in the opposite direction. That means if the bullet is moving in the forward direction, then the gun is supposed to move in the backward direction. This is why the gun moves backward when the bullet is fired. That is, the recoil of the gun occurs when the bullet is fired. So, the recoil of the gun is clearly explained by the law of conservation of linear momentum. Example 2. While firing a bullet, the gun is held close to the soldier. Or if you are firing a pistol, you should hold it firmly and steadily. Why? Let us see. From the above expression of the recoil velocity of the gun, that is capital B equals to minus small m into small b whole divided by capital M. Now suppose small m dash be the mass of the shooter. Then, to shoot the gun, the shooter holds his gun close to his soldier. The total mass of the gun as well as the shooter becomes capital M plus small m dash, so that capital B becomes minus small m into small b whole divided by capital M plus small m dash. Here, capital M plus small m dash becomes very large, therefore capital B, that is the recoil velocity of the gun, decreases. You know, as the recoil velocity capital B or the backward jerk due to the gun is reduced, the soldier of the shooter will not hurt and the shooter can easily hit the target with less recoil. So by increasing the mass, the recoil of the gun is reduced.